Right now, major retailers are actively paying their customers to get products later. Like, they will literally offer you digital credits or, I don't know, store discounts just to delay your shipment by a couple of days.
Yeah, it definitely sounds a bit backwards at first.
Right. On the surface, it sounds like terrible business to intentionally slow down your own service. But, in the world of high-stakes logistics, this strategy, it's called demand shaping, is often the only way a company can survive the actual physical limits of our supply chain. So, welcome to the deep dive.
Thanks. I'm excited for this one.
Yeah, today we are getting into the mechanics of how demand forecasts actually get translated into physical logistics capacity. And we're using the APCS Certified in Logistics, Transportation, and Distribution, or CLTD module, on demand management and supply as our guide.
It's such an essential perspective shift for people to make because, sales teams, they operate in a world of theoretical revenue.
Right, spreadsheets and goals.
Exactly. They project 1 million units sold, they hit their metrics, and then they celebrate. But logistics teams, meanwhile, they operate in a world of concrete, steel, and, strict Department of Transportation weight limits.
Yeah, which is way less theoretical.
Very much so. The transition between those two worlds is incredibly complex. I mean, 1 million units on a spreadsheet means absolutely nothing until you sit down and calculate the routing algorithms, the pallet density, the engineered labor standards required to physically move all that stuff.
Okay, let's unpack this because I want to start exactly at that transition point. Say I'm running a logistics service provider, an LSP. I can't just take my client's sales forecast at face value, right?
No, absolutely not.
Because a sales forecast is inherently optimistic. It doesn't really give me the data I need to, say, plan out my fleet of trucks.
Not just optimistic, it's entirely incomplete for logistics purposes. An LSP actually has to generate its own long-term freight volume forecasts completely independently.
Wait, really? They don't just use the client's numbers?
No, they can't. They look at macroeconomic leading indicators to model their future capacity needs. So we are talking about correlating things like building permits or initial unemployment claims or even consumer confidence indexes directly against their own historical carrier lane data. So, for example, if housing starts are down in the Sun Belt, an LSP needs to know how that specifically is going to impact flatbed truck capacity out of the Midwest, 6 months later.
That is wild. But, macro indicators only really give you a smoothed out average, right? They don't help you on a Tuesday when demand suddenly spikes 400% out of nowhere.
Yeah, macro data won't help you there at all.
Because the source material brings up these extreme micro events, like the massive surge in avocado demand right before Cinco de Mayo, or when a celebrity wears a specific dress and it just causes this viral run on inventory.
Right, which introduces extreme localized volatility. What's fascinating here is how incredibly specific and real world these forecasts have to be. The logistics forecast has to model capacity buffers for those exact crazy scenarios.
So for the avocado thing, what does that look like?
Well, for the avocado surge, they aren't just forecasting generic volume. They have to forecast highly constrained, specialized capacity. So they need refrigerated truck lanes, reefers. They call them converging on very specific border crossings for a super tight 10-day window.
And if they miss it?
If they miss that window by even a day or two, the product spoils. It's useless.
So it's basically like running a massive restaurant kitchen, right? It's not just predicting how many people will show up on a Friday night. It's knowing if they're all going to order the souffle at the exact same time and, whether the delivery truck bringing the eggs is going to get stuck in a snowstorm.
That is a brilliant analogy.
Yes. But wait, if you buffer for every possible viral trend or localized surge, aren't you just sitting on massive amounts of idle capacity? You can't just keep an empty warehouse and a fleet of trucks sitting on standby just in case a celebrity wears your client's dress. The overhead would completely bankrupt you.
Oh, you're absolutely right, which is why you don't buffer with physical assets just sitting around idle. You buffer through dynamic network design and elastic carrier agreements.
Okay, meaning what exactly?
Meaning you build flexibility into your routing guides. And remember, it's not just forward demand you're buffering for either. You also have to model for reverse logistics.
Oh, right. Returns.
Exactly. Defective products, seasonal returns, user error, all of that creates a backward flow through the supply chain. And that consumes inbound dock capacity and inspection labor.
Oh, man. So it's coming from both directions.
Right. If you forecast 1 million units going out, you better forecast the historical defect rate and plan your warehouse footprint for the 40,000 units coming right back.
And then you have to factor in external variables too, like I don't know, a blizzard shutting down a major rail hub right when those returns are peaking.
Yeah, the weather is a massive factor.
The variables are just staggering. Which kind of brings us to the actual execution. We have this incredibly complex, multivariable forecast. But what actually happens when we take these wild predictive numbers and try to turn them into physical reality?
Well, converting that math into physical reality doesn't happen all at once. The APS material breaks this translation down into three very specific planning horizons: strategic, tactical, and operational.
Okay, so if I'm looking at the strategic horizon, which is, what, 3 to 5 years out?
Roughly, yeah.
I assume I'm purely looking at capital expenditures at that point, like network footprint, facility locations, stuff like that.
Precisely. Strategic planning is all about the big picture: physical real estate and major network nodes. If the 5-year volume forecast shows a 30% increase in East Coast volume, you're using network modeling software to figure out, do we expand the existing Pennsylvania facility or do we build a brand new one in Georgia?
So you aren't scheduling daily labor here.
No, not at all. You are building the financial business case for a multi-million-dollar capital lease. Got it. Which logically flows into the tactical horizon, right? Once the building is there and we're looking about a year out, the focus shifts to operational design.
Yes. Tactical planning is medium term. You're negotiating your annual carrier contracts, locking in lane rates, securing base capacity on ocean freight and rail.
Okay, so the big moves, but for the upcoming year.
Right. But inside the four walls of the warehouse, tactical planning is heavily focused on standard hours modeling.
Standard hours modeling, meaning calculating the exact baseline time it takes an average worker to complete a specific task, like picking a case or loading a pallet.
Correct. If your tactical forecast projects processing 1 million units next quarter, you run that volume through your standard hours metrics. You calculate the exact engineered labor standards required to unload, put away, pick, pack, and ship.
Wow. It gets that granular a year out.
It has to. That tells you precisely how many full-time equivalents or FTEs you need to hire and how many forklifts you literally need to lease for that upcoming quarter. Okay, but the reality on the floor changes daily. If the tactical horizon secures the baseline labor and carrier contracts, the operational horizon must be where everything actually goes sideways. We're talking like weeks or days out, right?
Oh, yeah. Operational planning is where the abstract forecast becomes an absolute physical constraint. This is where TMS, Transportation Management System automation, takes over.
So the computers are running the show at this point.
Basically, the tactical plan set up the carrier contracts. But the operational plan uses rules-based routing guides to automatically tender loads to those carriers based on live weight, destination, and real-time cost.
Gotcha.
It's managing the daily dock schedule, handling customs clearance for an arriving container, and balancing the labor pool to handle, say, a huge Monday morning order surge.
Here's where it gets really interesting to me, because this is where the algorithms really earn their keep, especially with unit load calculations.
Oh, absolutely.
A forecast says we need to ship 10,000 units, but a truck doesn't care about units. It cares about cubic volume and gross vehicle weight.
Exactly. A unit is just a concept until it's boxed.
Right, so the operational system has to algorithmically convert those individual units into optimized unit loads, map them onto standard pallets, and then calculate how many of those pallets will physically cube out or weigh out a 53-foot trailer. It's like the world's most stressful game of 3D Tetris.
It really is a relentless mathematical balancing act. You might have 20% of your cubic volume left in a trailer, right? But if you're shipping dense industrial components, you've probably already hit the 80,000-pound highway weight limit.
So the truck is full by weight, even if it looks empty.
Right. And conversely, if you're shipping like uncompressed foam, you will cube out the trailer long before you hit the weight limit.
That makes sense.
So the TMS algorithms are constantly trying to mix light and heavy freight in the exact same load to maximize both metrics simultaneously.
Okay, but wait, isn't this assuming a perfect world? Like, algorithms can only optimize the capacity you actually have. What happens when a warehouse is already completely full or you simply run out of trucks?
Yeah, that is the million-dollar question.
Because if my warehouse is suddenly stuffed to maximum capacity because a new product launch overlapped with, stagnant legacy inventory, I can't algorithmically fix a building that has 0 empty pallet positions.
This raises an important question, actually. When capacity is maxed out, you have to shift from capacity planning to constraint management.
Okay, what does that look like?
The primary framework here is the theory of constraints, or TOC. It's built on the premise that any complex system is only as fast as its most severe bottleneck.
A chain is only as strong as its weakest link, kind of thing.
Exactly. You don't try to optimize the whole system. You focus entirely on the constraint using 5 specific steps. Identify, exploit, subordinate, elevate, and repeat.
Let's trace that through my overflowing warehouse scenario, because I want to see how this works. Step 1 is obvious. Identify. The warehouse is the bottleneck holding up the entire inbound supply chain.
Right. Easy enough.
Step 2 is exploit. Now, if my instinct is to just immediately go rent overflow storage space across town, I assume TOC says I shouldn't do that yet.
You definitely shouldn't. Elevating the constraint, which means spending capital to fix it, is step 4.
Okay.
Step 2, exploiting the constraint, means getting the absolute maximum throughput out of the existing bottleneck without spending a dime.
So in my warehouse, what does that mean?
It might mean aggressive inventory consolidation, like clearing out obsolete stock or even slowing down inbound vendor shipments just to keep inventory resting on the water or at the supplier's dock.
Oh, wow. Using the ocean transit time as like a floating storage buffer to buy yourself some time.
Exactly.
That makes total sense. But step 3 is where I think people get tripped up. Subordinate. I mean, that just sounds like a corporate buzzword. What does subordinating actually mean mechanically on the floor?
Subordinating is the most critical and honestly the most misunderstood mechanism in TOC. It means you deliberately pace every other non-constraint process in the supply chain to match the exact speed of the bottleneck.
Deliberately slowing things down.
Yes. Think of it like a multi-lane highway merging into a single lane for roadwork.
Oh, right. If you have 4 lanes of traffic merging into 1 lane, driving faster in those 4 lanes doesn't actually get you through the roadwork faster. It just creates a more massive, chaotic traffic jam right at the merge point.
Precisely. If your warehouse put-away team is the bottleneck, and they're only capable of processing, say, 10 pallets an hour, it doesn't matter if your inbound unloading team can process 20 pallets an hour.
Just because they have nowhere to put them.
Right. If the unloaders keep working at maximum speed, they will just flood the receiving dock with pallets. It creates physical chaos and actually slows the put-away team down even further.
Wow.
So subordinating means you explicitly tell the unloaders to slow down to 10 pallets an hour. You intentionally run your non-constraints below their maximum efficiency just to maintain smooth flow through the bottleneck.
That is so counterintuitive, but it's brilliant.
It really is.
So you only move to step 4, elevate, which is renting the outside storage or buying a fancy high-density rack system if exploiting and subordinating still don't give you enough throughput.
All right.
And then step 5 is repeat, because once you fix the warehouse, the bottleneck just moves somewhere else, right? Like a supply chain game of whack-a-mole. Suddenly, your outbound transportation network is the constraint.
Yes, and transportation constraints are notoriously difficult to elevate because they often involve external regulatory limits.
Oh, like laws.
Yeah. You might have the trucks and the labor, but you run into localized municipal laws.
Yeah.
A lot of European cities, for instance, have implemented strict environmental clean zones.
Right.
If your fleet doesn't meet the latest Euro emission standards, you physically cannot route those trucks into the city center. Or you face noise ordinances that just outright ban heavy commercial vehicles from operating during nighttime hours.
So you can't just algorithm your way out of a city ordinance. If you can't buy more trucks and you can't drive at night, you have to find hidden capacity in the network you already operate. The EPCS material emphasizes integrating inbound and outbound planning as a major unlock here, right? Like combining MRP and DRP systems.
It's one of the most effective strategies for uncovering hidden capacity. Because traditionally, inbound raw materials planning managed by MRP software and outbound finished goods distribution managed by DRP software, they operate in complete silos.
They don't talk to each other.
Exactly. So the DRP team dispatches a truck to deliver finished goods to a retail distribution center. Once it's empty, that truck deadheads back to the terminal. That empty return trip is called a backhaul, and it represents a massive loss of potential capacity.
But if the MRP and DRP systems are integrated, they can finally talk to each other. The algorithm sees that, hey, a raw material supplier is located just a few miles from that retail distribution center.
You see where this is going?
Yeah. So instead of deadheading back empty, the system routes the empty truck to the supplier, picks up the raw materials, and brings them back to the manufacturing plant. You've effectively doubled the utility of that single truck.
You're close, but the reality is actually even more complicated. Because you rarely have a perfect geographical match between your suppliers and your customers.
Oh, sure.
That is why the industry is moving toward collaborative transportation management. In Europe, we're seeing co-owned shipping hubs where fierce competitors actually share warehouse space and consolidate their loads.
Wait, competitors? Sharing space?
Yeah. They integrate their forecasting and capacity data so that an outbound truck might carry products from 3 different competing manufacturers to the exact same retail region. It minimizes empty miles for everyone.
It is absolutely fascinating that the physical limits of logistics are basically forcing competitors to cooperate. But I want to push back on this entire premise for a second.
Okay, go for it.
We've talked about optimizing standard hours, subordinating to constraints, integrating MRP and DRP, collaborating with competitors. But eventually, you just hit a wall. Peak season hits, every truck is booked, every warehouse is at 100% utilization. If you physically cannot find another truck or build another warehouse, how does the supply chain not just shatter? Like, can you just force the customer to change their behavior?
Well, it doesn't shatter because the final strategy isn't about managing capacity anymore. It is about altering the demand itself.
Okay.
If we connect this to the bigger picture, when physical capacity is absolutely tapped, companies utilize demand shaping. They use pricing, incentives, and marketing to actively manipulate customer behavior to align with their logistical realities.
So manipulating consumer demand to fit your truck schedule. How does a B2B supplier actually do that without angering their clients? I mean, B2B procurement is highly scheduled.
It works because B2B logistics relies on deep historical data to offer, like, surgical incentives.
Give me an example.
Okay, so if a supplier knows that their warehouse consistently hits a severe bottleneck every Tuesday afternoon because a cluster of major clients always submits their weekly orders, then they don't hire more Tuesday afternoon staff.
They just shape the demand.
Exactly. They offer those specific clients a 2% discount on the freight rate if they shift their standard order submission to Monday morning. The client gets a lower cost of goods, and the supplier smooths out their labor curve.
That is so smart. Another B2B strategy mentioned in the sources is forward shipping to dodge peak season freight constraints, right? Moving inventory to a warehouse near the customer months in advance, while transportation capacity is cheap and plentiful.
Yes, that's a huge one.
But here's my challenge on that. If every major supplier uses forward shipping to beat the Q4 peak season, aren't they just artificially creating a brand new peak season in Q3? How does the industry handle that shift?
That is a very real systemic issue, actually. And we do see peak seasons sliding earlier and earlier into the calendar year, specifically because of forward shipping. But the logistics networks prefer a longer, flatter peak in Q3 over an acute, catastrophic spike in Q4.
Oh, I see.
Forward shipping smooths the curve. It allows the final mile delivery, which is always the most constrained and expensive leg, to be executed as a short, local drop-off during the actual demand rush, rather than trying to secure cross-country long-haul capacity when rates are astronomically high.
Got it. So flattening the curve is always better for asset utilization.
Always.
So what does this all mean for the everyday consumer? Let's look at the B2C side, which takes us right back to where we started the show. B2C demand shaping feels much more psychological to me, because shipping millions of individual parcels is notoriously inefficient.
Oh, it's extremely inefficient. The B2C final mile is the most expensive segment of the entire supply chain. In B2C, demand shaping is heavily focused on algorithmic consolidation and delaying fulfillment. This is exactly why retailers offer you digital rewards like a $1 media credit if you select no rush shipping at checkout.
Right. So when I click that button to get my digital reward, the system isn't just saving on postage. What is the actual mechanism happening in the background there?
Well, the algorithm is looking at your order and realizing that fulfilling it immediately requires dropping a single small item into a large box, putting it on a half-empty truck, and expediting it through a sorting facility that is currently at its TOC bottleneck.
It's just a waste of capacity.
Huge waste. So by paying you $1 to wait, the system buys itself a 3-day window. And in those 3 days, the algorithm waits for a more optimal routing scenario.
Like what?
It might consolidate your order with another item you buy tomorrow. Or it waits until it can group your package with 50 others going to your specific zip code, which allows it to bypass the sorting bottleneck entirely and inject directly into your local post office.
That is incredible. And Amazon is famous for this with their Prime network. They offer incentives for a full basket approach. They are explicitly trying to train the consumer to hold their orders until they can fill a standard size shipping box, maximizing the cubic volume of that single shipment.
Yes, exactly.
They're essentially pushing the unit load optimization problem right onto the consumer's behavior.
Demand shaping really proves that the supply chain doesn't end at the warehouse dock. The consumer psychology is an active, malleable component of the logistics network.
It completely reorients how you view the economy, honestly. We started this deep dive looking at how LSPs use housing permits to predict flatbed capacity. We moved through the strategic modeling of warehouse footprints, the algorithmic intensity of cube and weight optimization, and then the counterintuitive brilliance of subordinating your workflow to a bottleneck.
And it all culminates in the realization that when the math and the physics are pushed to their absolute limits, the final lever a supply chain can pull is changing human behavior.
Which leaves you with a totally different perspective on your own shopping habits. Next time you are checking out online and the retailer offers you a tiny, seemingly generous incentive to delay your shipment by just a couple of days, ask yourself, are you just a savvy shopper scoring a discount? Or are you unwittingly acting as the final manipulated puzzle piece to help a massive distribution center clear a critical bottleneck in its theory of constraints cycle?
Something to think about next time you want that dollar credit.
Absolutely. Keep questioning the systems around you, and thanks for joining us on this deep dive.